Hey guys, this is our last set of notes for Unit 3. We're going to apply the sine and cosine laws, slide 19 and 20. You can fill out your table of contents. Today we're going to learn how to use, when we use which law. So at the top of your paper, you can put your title, Notes 3.2.3, apply sine and cosine laws. We're going to do some word problems and kind of decide when you're supposed to use which law. So the first one we'll talk about is when you use the law of sines. So use the law of sines when you know, okay, there's two options. Either two angles and one side. The side could be in between the angles or not in between. We call that angle, angle, side, or angle, side, angle. So this one has the side in between the angles, the other one doesn't. The other option is if you know, this is the bad word backwards one, two sides. And angle not between. So that bad words backwards. This is the ambiguous case. It could cause you to have no answers, one answer, or two answers. Then we're going to talk about when to use the law of cosines. When you use the law of cosines, you either know all three sides or you know two sides and the angle in between. So what's the difference between this and the bad word one is that the angle is in between the two sides. With the bad words, it is not in between the two sides. All right, next let's talk about how to do our trig word problems. Okay, so our trig word problems is what we're going to do today. The first thing you always want to do is draw a picture. You need to visualize what it's asking. So draw a picture with labels. Then you have to decide which law to use based on the information that is given. Were you given all three sides? Were you given two angles and a side? What were you given? Then you're just going to go ahead and set it up using your law and solve it. And your last step is just to make sure that the answer makes sense. Like you didn't get a negative answer for a distance. You didn't get an answer in the millions when it should have been, the other sides of the triangle were only in, 3 feet. So check that the answer makes sense. The last thing that we're going to write down on this little set of notes is the formulas for finding the area of a triangle. So we used it already when we did the law of sines, but I don't think we officially wrote it down in any of the notes part. But there's two formulas for the area of a triangle. Area equals 1/2 base times height. In order to do this one, you have to have a right triangle, or you have to know the height of it. Or the one that we learned was the new one. You can use it for any type of triangle. Doesn't have to be a right triangle. You don't have to know the height. Is AB sine of capital C. So that's what we're going to put into our notes, into our slide for our notes. Now we're going to go do some examples. So you need to have your workbook, Unit 3 workbook. Only have 3 examples. They're all word problems, and it's going to be on page 77. So example number 1 says a surveyor needs to measure the width of a building. He identifies 2 points E and F at ground level on opposite sides of the building. He walks to a point a distance away from the building, point G. He measures the distance from E to G as 284 feet, the distance from F to G as 322 feet, and the measure of angle G as 63 degrees. How wide is the building? Round your answer to the nearest foot, then determine whether it's reasonable in context of the problem. Okay, so first thing you always want to do is draw a picture. So don't be jealous of my drawing skills. Okay, I apologize if you guys can't draw as well as me, But here's my building, okay, and I'm gonna make this a bank. Not that it matters. But it says the surveyor needs to measure the width of the building. So this is what he needs to measure, right? He needs to measure how wide the building is. Well, he identifies 2 points at ground level on opposite sides of the building, and he calls these E and F. So that was like in the first sentence he told us this. Identifies 2 points, E and F, at ground level on opposite sides of the building. He walks to a point away from the building. Okay, so now he's away from the building, and this is point G. He measures the distance from E to G as 284 feet. And he measures the distance from F to G, so I'm just reading my word problem, F to G as 322 feet. And the measure of angle G as 63 degrees. How wide is the building? So this is our variable. This is the piece we want to find, is that side EF. Step 2 already tells us the answer to this, but we need to decide which law to use. Well, since they gave me 2 sides, right? 1 side, 2 side. You have to decide, okay, 2 sides, is the angle between or not in between? So when you look at this angle, the angle is in between those 2 sides. That means you're going to use law of cosines, okay? So if the angle is in between the 2 sides, you use law of cosines. So as a reminder of what law of cosines is, it's little c squared equals little a squared plus little b squared minus 2ab cosine capital C. Well, automatically, that whatever angle we have, we're going to call that capital C. Across from capital C is, I don't want to write in black, I'm sorry. Let's change colors. So across from capital C is going to be little c, and that means these 2 sides, doesn't matter which one's which, is little a and little b. So I'm going to plug those in. So little c is what I'm trying to find. Little a is 284 squared, plus little b is 322 squared, minus 2 times little a is 284, little b is 322, and then cosine of our angle is 63 degrees. So this little symbol right here, the problem tells me I'm going to be in degree mode. So with Desmos, I kind of found my little shortcut as to how I can do my problem a little easier. So what we can do now is we can actually take the square root of both sides in Desmos, and then that will give us our answer right away. So kind of like a little cheating step in Desmos is if you hit the square root button first and then just type everything in under it, then you'll get your answer. So it was 284 squared plus 322 squared minus 2 times 284 times 322 times the cosine of 63 degrees. I gotta make sure I'm in degree mode. Degrees is highlighted in green. Then we get 316.287532837. It asked us in the problem to round to the nearest whole foot. Nearest foot would be 318 because it's 318.2, so it stays. So 318 feet. So the question asked if that's reasonable. Well, the other numbers were 284 and 322, so that's perfectly reasonable for this side to be 300 and something feet because the other sides of the triangle were also about that big. So check, it is reasonable. I didn't get a negative number. I didn't get something in the millions. The building is only 4 feet wide, that kind of thing. Okay, let's go over to the back for example number 2. All right, example number 2 says Hideko is a pilot with a small 2-seater plane. She took off from the airport and headed south towards her hometown. After flying 70 miles, Hideko turned the plane 40 degrees to the west to avoid a large storm. She remained on this course for 95 miles before turning back 65 degrees to the east and continuing on to land near her hometown. How much further did Hideko fly than she would have if she would have remained on her original course? Determine whether your answer is reasonable in context of the problem. Okay, so this one, when I draw it, okay, she starts off at the airport, and it says that she's trying to fly south to her hometown. So I'm going to make south, this will be her hometown. So it says that she took off, and after flying for about 70 miles, my drawing is not going to be to scale. After driving or flying for 70 miles, Turn the plane 40 degrees to the west. So this is north, south, so this is east, this is west, right? So it turns 40 degrees to the west. So this angle, so she should have stayed just going straight, right? This should have been her original plan, but she turned 40 degrees to the west. So she continued on that course for 95 miles. Before turning back 65 degrees to the east. So the plane should have been going straight like that, but instead she turned 65 degrees and then headed home, right? So this was 65 degrees that she turned and then headed home, right? Continuing to land near her hometown. So the question is, how much further did she fly than if she would have remained on her original course? So this was her original course, right? Right. But instead she traveled this path right here. So we want to know how much longer that is. So we need to find a couple of pieces. We need to find this piece because we know this one's 70. We know this one's 95. So we need to find this one. And we also need to find this one. I'm going to call it Y because she went 70 and she should have just been able to keep going, but she wasn't able to. All right, so we need to find X and Y. We have two pieces that we need to find. So notice how the angle on the outside over here is the 65 because I turned, like I should have been going straight, but then I turned back 65 degrees. It's not drawn to scale. That means this angle right here is 115 degrees because these two angles are supplementary. They should add up to 180 degrees. If this angle is 115 and this angle is 40, then we can easily find this angle by subtracting 180 minus 115 minus 40 to get that this angle is 25 degrees. All right, so now I only know one side of my triangle, right? I know one side because I'm looking at this triangle right here. I know one side and I know all three angles. I was able to find all three. So what I'm going to do then is I'm going to use the law of sines. Anytime you know more than one angle, you're using the law of sines. The law of sines, okay, sides go on top and then the sine of the angle on the bottom. So I already know, or I only know one side. I know that one side is 95, okay, and across from that is 25 degrees. Then I can decide if I want to find X or Y. It doesn't matter which one. We'll find X, and across from X is my 40-degree angle. So that one's sine of 40 degrees. And then if you remember from last week, the way that we solved this, I'm going to do kind of like a little bit of a shortcut kind of thing. In order to get X by itself, I don't even have to cross multiply. I could actually just multiply on top both sides the sine of 40 degrees, and that will cancel from the denominator, and I'll get X by itself. I can go ahead and then just use Desmos and plug this in. 95 times the sine of 40 degrees divided by the sine of 25, and that will give me my answer for X. So I'm doing like a kind of like a shortcut. So I am in degree mode still because the angles that they gave me, 40, 65, those were all in degrees. So I'm just going to type in, what was it, 95 times the sine of 40 degrees. And then the whole thing, I have to put parentheses around it. Whole thing divided by the sine of 25. And that gives me 144.49. It didn't tell me where to round, I don't think. We'll just go one place after the decimal then. 144.5 because the 4 is going to round up. So this is 144.5. These are miles. So her actual path, what she took, was 70 miles plus 95 miles plus 144.5 miles. So that means that if I add those all up, I'm not going to like go to my Desmos. I already have what I get when I add them all up is 239.5 miles. Now let's go find her planned route, okay? So her planned route was to go 70 plus this Y. Well, remember on top you put sides over the sine of the angle. So we had that original 95 over the sine of 25 because that's what's across. Then we're going to find Y this time, which Y is across from the 115 degree angle. So instead of doing cross multiplying, I'm going to take my little shortcut of just multiplying both sides by the sine of 115 on top. Cancel so that I get y by itself, and then I'm just going to go ahead and type this into my calculator, Desmos, to get my answer. So 95 times the sine of, it was really close to this problem, I'm just going to edit this problem. It was 115 though, so 95 times the sine of 115 divided by the sine of 25 is 203.72. We're just going to round to 203.7. So then the planned, she should have just been able to go 70 plus the 203.7. So that's 273.7. So the did I make a mistake somewhere? 70, 144. Wait, 70 plus 95 plus 144. 70 plus 95 plus 144.5 is 309.5. That's what I get for like not doing it in my calculator. 309.5. Sorry, guys. Then what I have to do to find her, how much she went extra, I'm going to go ahead and subtract. So I subtract my 309.5 minus 273.7, and that should give me my answer. Minus 273.7. So she went an extra 35.8 miles. So 35.8 miles extra. All right, so to check to make sure this is reasonable, when you're in the plane, she went like 300 miles, whatever total. So 35 isn't that much extra miles to avoid. There was a storm right here. She didn't want to go through the storm. So it's not like you got an answer of a negative, right? Didn't get a negative answer. And it's not like we got an answer of 1,000,000 extra miles. So 35 is reasonable in context. Because the question asked how much further did she fly? So she should have just been able to go straight, which was 273.7. But instead she went 70, 95, 144.5. And so she went 35.8 extra miles. All right, last example. It says the Leaning Tower of Pisa, which is 55.8 meters tall, currently leans to the southeast. When the angle of elevation of the sun is 42 degrees, the tower is leaning towards the sun. The tower shadow is 57.9 meters long. How many degrees does the tower lean? Round your answer to the nearest degree. Determine whether your answer is reasonable in context of the problem. Okay, so I've never been to the Leaning Tower of Pisa, but I know that it's round, okay? And it says it's currently leaning southeast when the angle of elevation of the sun is 42 degrees and the tower is leaning towards the sun. So first I'm going to start by drawing my sun. So here's my sun. And my tower is leaning towards it. So the angle of elevation of the sun is 42 degrees, and then the tower shadow is 57.9 meters long. So is the shadow going to be on this side, or is the shadow going to be on this side, right? So when the sun's over here, then the shadow would be on this back side, right? So the angle of elevation, we did angle of elevation, is from the ground going up. So this is 42 degrees. It says the tower is 55.8 meters tall. That was in like the first sentence right here. The angle of elevation is 42, and then the shadow is 57.9. The question asks, how many degrees does the shadow lean? Okay, so how many degrees is it leaning? So we want to find this angle piece right here. All right, well, when we go to find this piece, we actually have one of those bad word backwards because we have an angle. No, we don't have a bad words backwards. We have, yes, we do have a bad words backwards. We have angle, side, side, ASS. That's the bad word. So we're going to have that ambiguous case, but we know that this angle X should be an obtuse angle because technically it should be a 90-degree angle. Like the ground and the tower should form a 90-degree angle, right? But it's leaning, so we have to find out how much it's leaning. So it's going to be a greater than 90-degree angle because it's leaning towards the sun. So it's going to be the obtuse angle. So what we need to do is we need to use the law of sine since we have that bad word backwards triangle. Remember, on top you always put your sides. We have two sides, 55.8 and 57.9. Well, across from the 55.8 is 42 degrees, so we have the sine of 42 degrees. And across from 57.9 is, well, it's not x, we're going to call it y. So sometimes you have to find the piece that you don't want to be able to find the piece that you do want. So keep that in mind. Sometimes you have to find part of the triangle that you don't want, but it will help you find the piece of the triangle you do want. So we're going to find this angle up here, even though it's not the angle we're trying to find, because once we know this angle and we know this angle, we'll easily be able to find this other angle. All right, so this one I can't do, my little shortcut. We're going to have to show all of our work. So I'm going to start by cross multiplying. I get 55.8 times the sine of y equals 57.9 times the sine of 42 degrees. In order to find y, I have a few steps. First, I'm going to divide by the 55.8 on both sides. I'm not actually going to like divide it out or use my calculator yet. I am going to be in degree mode. Usually if it's a real world problem, it's probably in degrees because that's what we usually use to measure, is like a protractor. But then in order to get y, I do have to take the sine inverse of both sides. So I'm going to let my calculator do the hard work for me. I'm going to do the sine inverse of 57.9 times the sine of 42 over 55.8. So I get my Desmos calculator. I'm in degree mode. I hit the sine inverse. I'm going to make a fraction. So on top was 57.9 times the sine of 42 degrees. And then on the bottom was 55.8. So it did say round to the nearest degree. So we're going to say that this angle, it says 43.9. So we're going to say that this angle is 44. Okay, so this angle right here, it's kind of hard to see, this angle y, my picture's so small, this angle y is 44 degrees. Well, like I mentioned earlier, if you know these two angles, you can easily find the angle that we did want because we know that all three angles of a triangle have to add up to 180. So 180 minus 44 minus 42, and we get 94 degrees. So angle X is 94 degrees. Well, remember what the question asks. How many degrees does the tower lean? So a tower should be perpendicular, right? Your tower should be standing straight to the ground and it should make a right angle. So this should be 90 degrees. So how much is it leaning if the angle is actually 94? If the answer is not 94, the answer is 4 because that's how much it's leaning. Leaning 4 degrees. So it should be at 90, but it's at 94. So that means that it's leaning 4 degrees towards the sun, to the southeast. All right, so for all your homework problems, you need to draw a picture, label it, decide which law to use, plug it in, solve it, check, make sure your answer is reasonable. So here is where we put our notes. It goes on slide 19, and then page 77 and 78 go on slide number 20. Your homework is word problems, starts on page 81. Okay, bye.